So when you take the sum of two knots, like we did here, look at the trefoil. What happened to the trefoil? The trefoil, we removed like this thing, right? And we're going to connect it to some guy like that, right? So what you can think of it is redraw this trefoil so it looks just like this. So we have some knot kind of drawn like this, but let's make it like a big loop like that. So you have we took one of the strands of the trefoil and pulled it out, and we can think of the trefoil as we have a normal loop and then a little tangled up thing. Just like with the extension cord, I could make my extension cord look really nice like the picture, or I could be like, usually what's going to happen, because my extension cord is long, remember, is I'm going to have this long extension cord with this little guy on it. So I guess I can draw it a little bit differently here. Challenge my drawing ability here. Let's see. Sorry. Let's try it more like this. Okay. So let's make it more like what I want there. I can take so it took a little while, but anyways, I can think of this little thing on this big loop. Okay? I could do the same thing with the figure 8 knot. I'm almost afraid to. But like you have the figure 8 knot, which is this, let's put it inside like a little box actually. Let's put it inside a little box. I guess you've been calling it J. And picture a little strand that comes out like that in my picture, right? And I guess when I do the connect the sum, it's gonna look like this, and this is the part that's gonna connect to the other knot, right? So this is part of my orange rectangle or whatever. This is the part that's gonna connect. But I can put this on the big loop. So it turns out connected sum of two knots will look like this, and then whatever's in my little box, I'll call it J. This is coming out like that. So I guess in general, in general, I could write it like this, K, and then it's so two knots. Like I guess the point is, you can think of the original knot as being this little guy on this big circle loop. Both of them you can think that way. And then when you take the connect sum, you can actually think of it as you put those little guys along the same big loop. And if you think about it, it makes sense. It's just shrink these big two strands so that they're really small, and you get these guys, these little guys. In the picture they're small, but I can make them big. And I have a picture like this. So connect the sum, you can, maybe a more natural way to think of connect the sum is you have a big loop, you put a knot in it, someone else wants to put a knot on it, and you open up the extension cord, you let them put their little knot in, you close it back up. Okay, that's a connected sum. Now if you think of it this way, the question of whether the connected sum is commutative is, can I somehow switch the position of J and K? Can I somehow switch the position of J and K? Maybe I shouldn't have erased that picture actually. But think of it this way. What happens if I shrink whatever's in here really, really small? Really, really small. Then what? Well, not so small it becomes a point. That would not be a valid ambient isotope. Yeah, so he says stop before it's a good point. Right? Actually, pretty good point there. So yes, so small, but not so small you're like, ruining it. Right?
It can pass through the other one.
Right, so what happens is now it's a little knot. Maybe you've tried it with the extension cord. Imagine this is like a big tangled up thing. Now you've made this like a really tiny thing. Now start sliding it along, slide it through here, and now it comes out the other end. Does that make sense? So let's, oh my goodness, let's try drawing. Let's try drawing that again here. Okay, let's see here. that. And then I guess we can do that. Okay. Okay, so imagine shrinking is really small. So now it's become this really small thing. Now start maybe probably even smaller here. Might need to really zoom in with that camera. Alright. Now you start sliding it along. You can slide the knot along. Just pull it along. Whatever's in that box, no matter how complicated, just keep pulling along, until it's like keeps sliding around. So at some point you're like sliding around. And it's like there. Right? You slide it through this other thing. Just keep sliding it around, and it comes out this end. It comes out here. You can make it bigger again now if you want. But it's been slid through. And what do we have? Now we have J, and this is the not K. The argument doesn't depend on that being the trefoil. That's important to note, right? It's just the point is it's just like a thing I can, pull along, right? So I switched the boxes. This is now K. That's J. So now they're in the other order. So it's obviously commutative. So what you say is not sum is commutative up to that ambiguity, of course. In the case when you can get different not sums, then what this means is if you can get two different knots, I guess I'll just say it real quickly. If you can get two different knots from doing some sum, then when you switch the order, you might, depending on what you did, you might get the other one. But there's still that same ambiguity. You're still restricted to those two knots from switching the order. So, anyways, that's a nice thing about not sum. And I guess think about this thing, because here's another problem. Can I have a situation like this? So I'll go over this next time. I have two knots like this. So say K is non-trivial, say it's like the trefoil or something, and say J is non-trivial, like the figure 8, so something we know is not trivial. Two of them along here. Can they somehow cancel each other out magically and get this? I asked before, but maybe something weird can happen. Maybe it can cancel, they can cancel out.
I'm not sure, but I feel like if you connect two knots, wouldn't that make it one strand that would be
Okay, so think about it. The question is, take anything, take a trefoil, or figure 8, or figure 8 and trefoil, or can they somehow magically?
Remember the tri-coloring thing? You said
Yeah.
like if you add other trefoils, no matter how many you add, it's always going to be tri-colorable.
Right.
So like
I
if
guess,
there's one trefoil, then it's always going to be tri-colorable.
Ah, good
Therefore, it's
point.
the
Okay,
unknowns.
it's a good point. So the good point is that definitely if you put a tri-colorable, there's an exercise in the book that says if K is tri-colorable, it doesn't matter what J is, the result is tri-colorable. So it definitely can't be the unknot. But say neither one's tri-colorable. I guess like figure 8, but you might try to use a coloring argument to argue that also. So let's just say two knots as yet undiscovered that are not tri-colorable. We don't know very much about it. I guess the general question we want to ask is, can two knotted up things cancel each other out and give you the unknot? So that's a very good point. Alright, so next time, okay, so I guess I'm sorry we went over, but make sure to read, might as well read ahead in the book. I wanted to talk about linking numbers. So look at 1.4. It's actually very pleasant. 1.4 is a very pleasant section.
So wait,
you'll find it's not very difficult to read, I hope. And then the exercises, you should at least be able to do a couple of, at least one of them based on linking number.
Did you go ahead and then go back?
Yeah, we did 1.1, 1.3, 1.5, and now we're doing 1.2, and we're going to do 1.4 next time. But if you look on the schedule in the book, or on the syllabus, it's listed in that order. So always make sure to look at the slide.
Like,
You don't have to answer all.